In this video, we'll be solving some problems under the head properties of systems. And we have the first problem here, which is defined by input and output relationship by y of n is equal to x of n into g of n, where x of n is my input, y of n is my output, and when x of n is given as an input to a system, I get this is x of n, I get output as y of n, which is from the previous videos we have come to know that there is a transformation happening on x of n which will give us y of n. So the transformation here is just the multiplication by a another signal which is g of n. Now we'll be categorizing this system into linear, causal, time invariance, memory and stability. Now for the first case I'll be taking linearity. From the basics of linearity we know that if you have a transformation on x of n yielding you y of n, if input is weighted sum of two or more inputs, that is a x1 of n, b x2 of n, must give us a y1 of n plus b y2 of n. This is the definition of linearity property for a system. Now what we need to do here is, in place of x of n, I need to replace it by weighted sum of two signals. So what is our input output relationship? We have it here. So t into a x1 of n plus b x2 of n will give us, in place of x of n, I need to substitute it as a x1 of n plus b x2 of n, because my input is replaced by weighted sum, into g of n. I have it here. So this is a into x1 of n into g of n plus b into x2 of n into g of n. This is nothing but a into y1 of n plus b into y2 of n, because y of n gave you x of n into g of n. G of n is a constant, so it is independent of the changes in y or x. So y1 of n will give us x1 of n into g of n, and y2 of n is x2 of n into g of n. So we have on the left hand side a x1 of n plus b x2 of n. On the right hand side we have a into response of the system to x1 of n plus b into response of the system to x2 of n. So since this condition is satisfied for the system is linear. Now coming to causality, as we know from the basics of causality that output at one instant should depend upon input at the same instant or the previous instant. See, we have, what is the relationship between input and output here? Y of n is equal to x of n into some factor, constant factor. Now, y of 1, if I put the value y of 1, it is x of 1 into g of 1. So output at one instant depends upon the input at the same instant or the previous instance. So y of 2, if I put x of 2 into g of 2. So here output at present instant depends upon the input at the same instant. So the system is said to be causal. From the definition of causality, it says that if output at one instant depends upon the input at the same instant or the previous instant, the system is said to be causal. So in this criteria holds good here. So the system becomes causal. Now time invariance. The property of time invariance is that a transformation on x of n minus n naught should give us y of n minus n naught. That is, a shift in the inputs should result in the same shift in the output. Now what is transformation on x of n minus n naught? It is, see, this relationship can be written as transformation on x of n, because y of n is transformation on x of n. Now transformation of x of n minus n naught, that means I am replacing x of n or shifting x of n by n naught. So wherever I have x of n, it will be replaced by n minus n naught into g of n. Only there will be a shift in n naught. Now what is the right hand side here? Y of n minus n naught. So y of n is equal to x of n into g of n. So y of n minus n naught is, wherever I have n, I need to replace it by n minus n naught. So x of n minus n naught into g of n minus n naught. Notice the difference. See, transformation on shift on x of n will only be reflected in the input, not in the constant term, but shift in the output will be reflected here. So these two conditions, transformation on x of n minus n naught is not equal to y of n minus n naught, as we can see here. That means a shift in the input will not result in the same shift in the output. So the system is time variant. So system is not time invariant, or I can call it as time variant system. Now coming to memory. So when do we say that the system is having memory? When output at one instant depends upon the input at the past instant or the future instant. See, but not the present instant. See here, output at one instant depends upon the input at the same instant. As we can see, you have a linear relationship. Y of 1 will be equal to x of 1. Y of 2 is equal to x of 2. We are looking into only input and output. We are not bothered about the constant terms. So output at one instant depends upon the input at the same instant, but not the past or the future instant. So the system is said to be memoryless. A system is said to have memory when output at one instant depends upon the input at previous instance or the future instance. That is, y of 2 is equal to x of minus 1 or x of 4. If it was there, then the system would be having some memory, but here it is not having memory, so it is memoryless system. The last one is stability. Now what is the stability criteria? It is BIBO stability. Now we assume that, or we presume that the input is bounded. That means the amplitude of x of n is equal to some value bx which is less than infinity. So this is how I bound my input. Now I am checking whether my output is bounded. That is the meaning of bounded input, bounded output stability. You bound your input and check whether your output is bounded. Y of n is equal to, what do you get? Modulus of y of n is modulus of x of n and modulus of g of n. Now x of n modulus means what? The value of x of n is bounded, that is, it is less than infinity, but we do not have control over g of n. So for y of n to be bounded and for the system to become stable, the necessary and sufficient condition is g of n, magnitude of g of n must be less than infinity. So if magnitude of g of n is less than infinity, my output is also bounded, because input we have presumed that it is bounded, and if magnitude of the constant factor g of n, if it is bounded, then that is, if it is less than infinity, then my output will also be bounded. So the stability criteria completely depends upon the magnitude of g of n. Now the second problem, I've taken a continuous time signal in which input and output relationship is given by y of t is equal to e power x of t, where x of t is the input and y of t is output. Now linearity property, to check linearity property, so my input should be a weighted sum of one or more signals. So if I take this, and this can be represented as a transformation on x of t, this whole, the transformation is my input is getting raised to the power e. So if I give weighted sum of two or more signals, in this case it is two signals, then x of t must be replaced by that value. So it is e power a into x1 of t plus b into x2 of t. Now, from the basics, for if the system has to satisfy linearity condition, transformation on a x1 of t plus b x2 of t must be a into y1 of t plus b into y2 of t. That is nothing but a into transformation on x1 of t plus b into transformation on x2 of t. So I should be getting a into transformation on x1 of t is what? E power x1 of t plus b into transformation on x2 of t is transformation on x2 of t is e power x2 of t. Wherever, if you have x of t, wherever you have x of t, replace it by x1 and x2, you get this. So I should be getting this in the right hand side, but what do I get here is e power a x1 of t into e power b x2 of t, which is not same as this case. So the system is non-linear. By looking at the input-output relationship only, we'll get to know whether the system is linear or non-linear, because exponential input raised to the power exponential, we know that exponential signal, how does it look like? It is if it is negative going exponential, it is like this, and if it is positive going exponential, it is like this. So it is, exponential signal is never linear, so we get the system to be non-linear. The second one would be time invariance. So time invariance property says that a shift in the input should result in the same shift in the output. So what is the shift in the input? Transformation on x of t, we know it is e power x of t. What is transformation on x of t minus t naught? It is exponential of x of t minus t naught. Now what is y of t minus t naught? Y of t minus t naught is replacing t by t naught. It is exponential of x of t minus t naught. Now these two are equal, so the system is, this property, this condition holds good here, so the system is time invariant, meaning if there is a shift in the input, there is a corresponding shift in the output as well. Now other two properties are causal and memory. A system is said to be causal if input at one instant depends upon the output at the same instant, or rather it is output at one instant depends upon the input at the same instant. So I can write y of 1 is equal to exponential of x of 1. That means what is the relationship between input and output and input? Output at one instant, that is y at 1 is equal to x at 1 raised to the power exponential. So output and input relation is, if output at one instant depends upon the input at the same instant, so it is causal. The system is causal. Only the catch criteria for causality is output at one instant should not depend upon input at the future instance. Now the next is memory. A system is said to be having memory if output at one instant depends upon input at the past or the future instance. So here it is x of 1. Output at instant 1 depends upon the input at the same instant, which is not the criteria for a system to be having memory. So the system is said to be memoryless. So when would this system be having memory? So when, if y of 1 was equal to e power x of minus 2 or minus 3, that means past values, or y of 1 was equal to exponential of x of 3 or 5 or higher values, that future values, then the system would be having memory. But in this case it is memoryless. Now coming to the last topic, that is stability. Now it is again bistable. So what is the definition of bistability? We presume that x of t is bounded, that is it is having some value bx, you can take any value here, bx, which is less than infinity. Now what is the output if input is bounded? Y of t is what? Exponential of x of t. Now x of t value is bounded, that means it is less than infinity. So exponential to the power a bounded value will always be some value which is less than infinity. Because x of t is bounded, this exponential term will eventually lead to infinity only when x of t is infinity. But we have already assumed that from the definition of bistability is that x of t is bounded. So if x of t is bounded, output is also exponential to the power bounded value is also bounded. So the system is stable. So the system represented by input-output relationship, this system is nonlinear, time invariant, causal, memoryless, and stable. Now the third problem is x of t is equal x of t by 2, that is equal to y of t, and which also can be represented as transformation on x of t. Now again, the set of properties which we'll be going through, the first one has to be linearity property. So according to the linearity property, if input is weighted sum of two or more signals, a x1 of t, b x2 of t, I need to replace x of t by my weighted sum. So a x1 of t by 2 plus b x2 of t by 2, which is nothing but a into y1 of t plus b into y2 of t. So because y1 of t is what? x1 of t by 2, y2 of t is x2 of t by 2. So if input is weighted sum of two or more signals, output is the response to individual signals. So the system is linear in nature. Second one is time invariance. So time invariance property is x of t minus t naught, that is, if there is a shift in the input, there should be corresponding shift in the output as well. Now the left hand side, if I take x of t minus t naught is x of t by 2 minus t naught, because I am just shifting my input by amount t naught. Now y of t minus t naught would be x of, wherever you have a t, you replace it by t minus t naught. So it is t minus t naught whole divided by 2. Now these two are not equal, hence it is not time invariant, rather it can be called as time variant system. The third one is causal. Now output at one instant, if it depends upon the input at the same instant or the past instant, then it is called as a causal system. Say if y of 1 is x of half, that means output at one instant depends upon the input at the previous instant. This is right. If I take y of minus 1, I would be getting x of minus half. Again, this minus 1 is a present instant, minus 1, and minus half is a future instant. So for causality, the output at one instant should depend upon the input at the same instant or the past instant, but not the future instant. So this is a condition wherein output at one instant, because on the number scale 0, minus 1 and plus 1, minus half comes somewhere between 0 and minus 1. So minus half is a future instant compared to minus 1. So y of minus 1 is equal to x of minus half. It is future instant, so it is non-causal. Next one is memory. A system is said to have memory if output at one instant depends upon the input at past or future, but not the present instant. That means y of 1 should not be related to input as x of 1. So y of 1 is x of half, y of minus 1 is x of minus half. Now that means output at one instant depends upon the input at the past instant. This is 1 and half. Here output at one instant depends upon input at future instant. This is also is valid. But what happens when y of 0, we give t as 0? Y of 0 is x of 0. That means output at one instant depends upon the input at the same instant. This is not the criteria for a system to be having memory. So this system will have memory for all other values of t except for t is equal to 0. So we can write it is having memory except for t is equal to 0. The last one is stability. So we take input as bounded, x of t is bounded, that is equal to some variable bx which is less than infinity. Now we are checking whether my output is bounded. Y of t, modulus of y of t is modulus of x of t by 2. Now since x of t is bounded, x of t by 2 is the expanded version of x of t, so it will also be equal to some variable b of y which is less than infinity. Hence the system here is stable. So system represented by input-output relationship y of t and y of t is equal to x of t by 2 is linear, time variant, non-causal. It is having memory for all the values of t except for t is equal to 0, and it is stable. I've solved 3 problems in this video under properties of systems. I'll be solving some more problems in the upcoming videos. Thank you.